In this video, we're going to cover the energy-momentum tensor, which is the main object on the right-hand side of the Einstein field equations, and acts as the source of curvature in space-time. In the last video, I talked about how we can take Poisson's equation from Newtonian gravity and reformulate it in terms of space-time curvature, setting the 0,0 component of the Ricci tensor to be proportional to the mass density. However, this equation won't work for general relativity, because neither R00 nor the mass density are invariant in all reference frames. If we have a mass m in a volume V at rest, then the mass density is ρ. If we look at this same setup in a frame where the volume is moving, the volume could be length contracted to be half its size, meaning the mass density in the moving frame will double in size. So the mass density depends on the frame of the observer. It turns out that we can generalize the mass density to a tensor called the energy-momentum tensor, which is agreed on by all reference frames in special and general relativity. The energy-momentum tensor tracks the flux of energy and momentum through space-time. This can be confusing to understand at first, so we're going to work up to it in small steps. I'm going to spend about 10 minutes covering a simpler related concept called the number-flux 4-vector n, starting in Galilean relativity and then again in special relativity. I'll also talk about how the number-flux 4-vector can be used to describe a conservation law for the number of particles in spacetime. Next, we'll cover the full energy-momentum tensor, and in a similar way, we'll see how we can use it to describe conservation laws of energy and momentum in spacetime. Finally, we'll talk about the energy-momentum tensors for dust-like and perfect fluid distributions of matter. So this video is a bit long, but my goal is to give you a good intuition for the energy-momentum tensor, instead of just throwing equations at you. To begin, we're going to consider the number-flux vector in Galilean relativity, without any length contraction effects. We'll consider special relativity and length contraction later. So the number-flux 4-vector has 4 components. The time component gives the number density for a group of particles, and the spatial components give the current densities for the 3 spatial directions. I'll explain what this means using pictures. To calculate a density over space in one dimension, this is just a quantity per unit length. For example, charge density in one dimension is the amount of charge per unit length. Mass density is the amount of mass per unit length. And number density is the number of something per unit length. So if we have 4 particles in a unit length, then the number density would be 4. Another important concept is one-dimensional current, which is the amount of something passing through a point in a unit time. For example, electric charge current is the amount of charge that passes this point per second. Mass current is the amount of mass crossing this point per second, and number current is the count of objects passing this point per second. Now, it seems like density and current are 2 separate concepts, but they're actually related. We can visualize both number density and number current on a space-time diagram. Let's say that we have a collection of stationary particles. Their world lines would all be vertical, like this. To get their one-dimensional density in space, we pick some constant time t and count the number of particles in a unit length, delta x. This is the same thing as drawing a line segment of length 1 at a constant time, and counting how many particle world lines cross it. So if 4 world lines cross this line segment, then the number density is 4 particles per unit length. Now let's say that we have a collection of particles moving to the right with constant speed. To find their current in the x direction, we need to know how many particles are passing through a point in 1 unit of time. We can calculate this by picking a constant position x and counting the number of world lines that cross a line segment for a unit time, delta t. The particles attached to each of these world lines correspond to particles that have crossed this exact point during 1 unit of time. So if 2 world lines cross this line segment, this means that the number current in the x direction is 2 particles per unit time. Now, let's look at the case where we have 2 spatial dimensions, x and y, as well as time. On a spacetime diagram, a bunch of stationary particles would have vertical world lines like this. To get their 2-dimensional number density, we just count the number of particles in a 2-dimensional unit square in the xy plane, at some constant time. This is the same thing as drawing a square at a constant time in the xy plane and counting how many world lines pass through it. So if we have 4 world lines crossing this square, then we have a 2D density of 4 particles per unit area. Now, if we have a bunch of particles moving in the x direction, we can find their x current density. This is the number of particles crossing a unit length per second. We can get the x current density by taking a unit area in the time y plane at some constant x value and counting how many world lines pass through it. Basically, the y direction of the square is our unit length that we're counting the current density in, and the time direction of the plane is the unit time that we're using to measure the rate of flow. So counting the number of world lines that cross this plane will give us the x current density, the number of particles crossing this line per unit length in a unit of time. If we wanted to measure the current density in the y direction instead, we would just count the world lines crossing a unit square in the time x plane instead, at some constant y value. Now, if we go to full 4D spacetime, with time and all 3 spatial dimensions x, y, z, we unfortunately can't visualize the paths of particles easily on a spacetime diagram. The 3D number density would be the number of particles inside an xyz unit cube at some constant time. On a 4-dimensional spacetime diagram, this would be the number of world lines that cross a 3D xyz unit cube at some constant time. But again, we can't easily draw this on paper. The number current density in the x direction is the number of particles that cross a unit square in the yz plane, in a unit of time. This would be the number of world lines that cross a 3-dimensional time yz unit cube, where the yz gives us the unit square for measuring the current density, and the time length of the cube gives us the unit time that we're measuring the current over. The y number density would involve counting world lines in the time xz unit cube, and the z number current density would involve counting world lines in a time xy unit cube. But again, these are not easily drawn. So at first glance, it seems like the 3 possible number current densities in the xyz directions are fundamentally different than the number density we measure over 3D space, at some constant time. But geometrically, these 4 concepts are all just different versions of the same thing. For spatial number density, we just count the number of particles per unit xyz cube at a constant time. For x number current density, we count the number of particles per time yz unit cube. And for y and z number current densities, we count the number of particles per time xz unit cube and time xy unit cube. All 4 of these quantities are measured by counting the number of particles in a 3D box in space-time, and they make up the 4 components of the 4 vector that we call the number-flux 4 vector. For the purposes of this video, the word flux means the same thing as current density. Different areas of physics might define the word flux a little bit differently, but for this video, the word flux just means the number of world lines that cross a unit box in a spacetime diagram. Or in other words, it's the number of particles inside a box when we hold one of the spacetime coordinates constant. Now, let's say that we have a bunch of particle world lines and we draw a box in spacetime. If we have 5 world lines that enter this spacetime box, then we must also have 5 world lines that leave this spacetime box. This is because particles don't get created or destroyed, and world lines can't just spontaneously start or stop. The mathematical version of this statement is that the 4-dimensional divergence of the number-flux 4 vector is 0, given by this formula here. This is what we call a continuity equation, because it relates the density of particles over time and the spatial divergence of the particle current density. Basically, if particles are leaving a spatial XYZ box with positive divergence, the density of particles in the box must decrease over time. And if particles are entering an XYZ box with negative divergence, the particle density must increase over time. A more compact way of writing the continuity equation using the Einstein summation notation is like this. To introduce some new notation, we sometimes denote the density in the rest frame of the particles as a lowercase n. This is called the rest number density. In Galilean relativity, this is the same thing as the ordinary number density in all frames. But we'll see later in special relativity, number density can change depending on the frame. Now, you'll notice that for the x number current density, also called the x number flux, we can multiply and divide by delta x. This lets us rewrite the term as the spatial density, or the time flux, times the velocity of the particles in the x direction. We can do something similar for the y and z directions. So this is an alternative way of writing the number flux 4 vector. So we can rewrite the components of the number flux 4 vector in terms of the rest number density small n and the particle velocities. But we know that the velocities of objects are relative and depend on the reference frame. If we have some stationary particles and a car moving to the right, both the stationary frame and the car reference frame will measure the same number density of particles, 4, because their x-basis vectors are the same, and lengths don't change in Galilean relativity. But while the stationary frame measures a current of 0, the moving car measures a current of 2. So in Galilean relativity, current measurements depend on the reference frame, but density measurements are the same for everyone. If we upgrade to special relativity, which uses Lorentz transformations instead of Galilean transformations, we have to deal with length contraction, which does make the number density different in different reference frames. So when the stationary frame measures a number density of 4 here, the moving frame measures the number density along a diagonal line of constant ct tilde, using a unit length of delta x tilde, which results in a higher number density of around 5. Specifically, the number density in the rest frame is increased by multiplication by the gamma factor for the moving frame. The gamma factor takes length contraction into account so that there are more particles per unit of space. We can also measure the x current density at a line of constant x tilde, and this ends up being about 3. Although the exact numerical value is the Galilean result of 2 multiplied by the gamma factor, which takes time dilation into account. So we can see how to get the components of the number flux 4 vector using pictures, but we can also get the components using algebra. In Galilean relativity, we know that the 4-position vector s looks like this, with the 4 components being t, x, y, z. And the number flux vector looks like this, with the number density multiplied by a vector of 1 and the 3 spatial velocities. In special relativity, the 4-position vector s looks the same, except we multiply time by the speed of light c to make the units consistent for all 4 components. For the number flux vector, we also multiply the time component by c to make the units consistent. To take the effects of time dilation and length contraction into account, we need to multiply each of these components by the gamma factor. We can see now that the number-flux 4 vector in special relativity is just the number density of particles in the rest frame multiplied by the 4 velocity of the particles. So the full 4 vector looks like this. Now, the density of particles in their own rest frame, small n, is agreed on by all frames of reference. This means that if we know how to transform the components of the 4 velocity in different frames, then we also know how to transform the components of the number-flux 4 vector, because the rest number density doesn't change. So we transform the number-flux 4 vector just by using the standard Lorentz transformation matrix that we've seen all throughout this video series. With the number-flux 4 vector, we're counting the total particles, which is a single number, inside a box of size 1. Because of this, the number-flux 4 vector is enough to describe the flow of particles in all 4 spacetime directions. But what if we wanted to count the total 4 momentum, which is a vector quantity, inside a box of size 1? Another 4 vector is not enough to describe the flow of 4 momentum inside a box. Instead, we're going to need a 4x4 tensor called the energy momentum tensor, which describes the flow of the 4 components of 4 momentum in all 4 spacetime directions. So to get the 4x4 energy momentum tensor, we're going to use the same strategy of counting particles in a box that we used for the number-flux 4 vector. Except this time, we're going to be counting 4 momentum inside of a box instead of just the number of particles inside the box. We can find the components of the energy momentum tensor as follows. The T alpha beta component is equal to the flux of alpha momentum going through a unit box at a coordinate of constant beta. This probably sounds pretty abstract, so let's look at some examples. Let's go back to our 2D spacetime diagram for time and x, with particles moving in the positive x direction. Each of these particles has their own 4 momentum vector that they are carrying with them. Let's look at the one-dimensional 4 momentum density, which is the amount of 4 momentum at a constant time, ct, per unit length delta x. So inside this unit length at constant time, all of these 4 momentum vectors have a time component and an x component. If we look at the total of the time components, this gives us the time-time component of the energy momentum tensor. This is the total time momentum crossing a boundary of constant time. We can also look at the total x momentum in this unit length. This gives us the x time component of the energy momentum tensor, which is the total x momentum crossing a boundary of constant time. We can also look at the total momentum contained in the x flux of particles, which is just the particles that pass through some point at a constant x value in 1 unit of time, which is represented by a vertical line segment. The total time components of these 4 momentum vectors gives us the time x component of the energy momentum tensor, the total time momentum crossing a boundary of constant x. And the total x components of the 4 momentum vectors gives us the xx component of the energy momentum tensor, the total x momentum crossing a boundary of constant x. It turns out that the energy momentum tensor is symmetric, so T alpha beta equals T beta alpha. We can see this in our spacetime diagram geometrically. The amount of x momentum coming out of this surface of constant time, the xt component, is equal to the amount of time momentum coming out of this surface of constant x, the tx component. We can generalize this approach to 4-dimensional spacetime by looking at the amount of 4 momentum flux through a 3-dimensional unit spacetime box instead. If we take an xyz box of unit volume at some constant time, then we would be looking at the alpha time components of the tensor, since time is constant. Now let's look at the 4 momentum vectors of the particles living inside this volume. We can count up the total time momentum, x momentum, y momentum, and z momentum. These give the tt, xt, yt, and zt components of the energy momentum tensor. We could also take a unit box made of time, y, and z with a constant x component to examine the flux of form momentum in the x direction. This would be the alpha x components of the energy momentum tensor, since the x coordinate is held constant. We look inside the box and calculate the total time, x, y, and z momentum. This gives us the tx, xx, yx, and zx components of the energy momentum tensor. We can use a unit time xz box at constant y to get the alpha y components, and a unit time xy box at a constant z to get the alpha z components of the energy momentum tensor. So these 16 components give us the full description of how form momentum is moving through space-time. A bunch of particles moving through space-time will each have their own world line. The result is like a river of form momentum, which looks a little bit like spaghetti. If we take a cross-section of this spaghetti using a unit box at a constant coordinate, then the total form momentum in this box will give us 4 of the 16 components of the energy momentum tensor. So the energy momentum tensor T is like a machine that takes 2 unit vectors as input and outputs a momentum density. T acting on v and w gives us the total momentum in the v direction inside a unit 3D spacetime box perpendicular to the w vector. The T alpha beta component is just what we get when the momentum direction is a basis vector E alpha and the 3D spacetime box is denoted by a perpendicular basis vector E beta. So we can think of the alpha beta components of the energy momentum tensor as the flux of alpha momentum crossing a unit volume of constant beta. But we should remember that the time component of form momentum is the energy of a particle. So the first row of the energy momentum tensor, where alpha is the time index, is really about the energy of the particles. Also, the phrase flux across a volume of constant time is really just a fancy way of saying the word density across space, which is the amount of stuff in an XYZ unit box at a constant time. So the first column, where the beta is the time index, is really about densities across space. So we can also interpret the components of the energy momentum tensor as follows. The time-time component is the energy density, and the rest of the first row is the flux of energy in the different spatial directions. The rest of the first column is the density of spatial momentum at a constant time. And the remaining 9 components are the flux of spatial momentum in the 3 spatial directions. The 3 diagonal elements are called pressure, where momentum is perpendicular to the surface that it's crossing. Pressure has the tendency to squash and stretch objects. We say that these are equal to pressure because they're equal to momentum divided by time over a unit square. And since momentum divided by time is just force, this is force over a unit square, which is the definition of pressure. The off-diagonal components are called the shear stress, where the momentum is parallel to the surface it's crossing. These have the tendency to shear or rotate objects. It turns out that we can express the laws of conservation of energy momentum by taking derivatives of the energy momentum tensor. For now, let's pretend we're working in special relativity in standard Cartesian coordinates so that we don't have to worry about the connection coefficients in our derivatives. Let's take the components in the top row of the energy momentum tensor. These tell us the flux of the time component of momentum, or energy, through various boxes in each coordinate direction. Now let's take the divergence of these components. So we differentiate the 4 components by time, x, y, and z respectively, then add them all together. If we view the time and space portions of the equation separately, it kind of looks like a continuity equation, where if the energy is flowing out of a box, then the energy density must decrease over time. Or if the energy is flowing into the box, then the energy density must increase over time. To make this continuity equation make sense, we must set this expression equal to 0, so that energy can never be created or destroyed. It can only flow in and out, which results in changes to the energy density. So when we say that the divergence of the first row of the energy momentum tensor is 0, we are basically demanding that energy be conserved. We can also take the divergence of the next row and force it to be 0 as well. This gives us a continuity equation for x momentum, which forces the x momentum to be conserved. Basically, if x momentum is flowing out of a time yz box, then the x momentum density must be decreasing. And if x momentum is flowing into a time yz box, then the x momentum density must be increasing. Setting the divergence of the last two rows of the energy momentum tensor to 0 gives us continuity equations for y and z momentum, which forces y and z momentum to be conserved. We can rewrite the four equations of conservation of energy and momentum more compactly using four Einstein summations, where we sum the derivative index with the second index of the energy momentum tensor. We can then summarize all four equations as a single summation, where we allow the first index mu of the energy momentum tensor to be any of the four spacetime indices. You might see this summation written in this notation, which looks similar to taking the divergence of a vector, only this time we're taking the divergence of a tensor. This notation is a bit strange, but it just means that we treat each row of the tensor as a vector and take the divergence of each one, giving us four divergence equations. Also, I said earlier that I used a simplifying assumption of a coordinate system where the connection coefficients are 0. If we want a law of conservation of form momentum that works in all coordinate systems, we must use a correct covariant derivative, and take the derivative of the basis vectors as well. This derivative has two summations with connection coefficients because the energy momentum tensor is a rank 2 tensor. The components of this derivative are summed using this notation with the nabla symbol, or this notation with the semicolon symbol, instead of the partial derivative only. This is the proper law of conservation of form momentum that works in all coordinate systems. Now, it should be noted that, in general relativity, this conservation of energy momentum equation only applies locally, at an infinitesimal point. In large regions of spacetime, there is generally no law of conservation of energy momentum. For example, in an expanding universe, the wavelengths of photons expand along with space, redshifting them to lower energies. Energy is simply lost in this case, and is not conserved. I'm not going to get into the mathematical reasons for why energy momentum is not conserved in curved spaces in this video, but it's related to there being no sensible way to add four momentum vectors in a large region of spacetime, because parallel transporting them to the same tangent space will depend on your choice of parallel transport path. Before this video ends, I'm going to give two quick examples of real energy momentum tensors, the dust and perfect fluid energy momentum tensors. A dust-like distribution of matter is a collection of particles that are not exerting pressure on each other. Let's say that we know each particle has form momentum p, and their densities are described by a number-flux 4 vector n. If we want to know how much form momentum is located inside a unit xyz cube at some constant time, we just multiply p by the number particle density, which is the time component of n. Since p is the form momentum of each particle, and nt is the number of particles in a unit xyz box, then p times nt will give us the total form momentum inside the unit xyz box, which are the alpha t components of the energy momentum tensor. If we want to know what the form momentum flux in the x direction is, this is the form momentum contained in some unit time yz cube at a constant x. And we get this by multiplying the form momentum p by the x flux, which is the x component of n. So basically, if we want to know the flux of form momentum in the beta direction, we just multiply the 4-momentum vector by the beta component of the number-flux 4 vector, which gives us the beta column of the energy-momentum tensor. In terms of arrays, the dust energy-momentum tensor is the outer product of the 4-momentum and the number-flux 4 vector. Using more abstract tensor language, the energy-momentum tensor for dust is just the tensor product of the 4-momentum and the number-flux 4 vector. This helps explain why the energy-momentum tensor is rank 2 and needs 2 transformation matrices, one for each index, when we change coordinates. One matrix changes the components of the momentum vector, and the other matrix changes the spacetime orientation of the unit box we use to compute momentum density. The energy-momentum tensor itself is invariant and agreed on by all coordinate systems, but the components we get will depend on the basis vectors used to measure the momentum densities. For the dust energy-momentum tensor, we can also rewrite the 4-momentum as the rest mass m times the 4-velocity vector, and the number-flux 4 vector can be rewritten as the rest number density n times the 4-velocity. And we get this matrix times the rest mass density rho, which is the rest mass times the rest number density. In the case of stationary dust, where the spatial components of the 4-velocity are 0, the dust energy-momentum tensor only has one component, the energy density, which is the mass density rho times c squared. This is sort of like E equals mc squared per unit volume. Now, not all energy-momentum tensors are dust-like, where we can write it as a tensor product of 4-momentum and the number-flux 4 vector. For example, if the particles exert equal pressure on each other in all directions, then the xx, yy, and zz components of the energy-momentum tensor will be equal to a pressure p. This is the energy-momentum tensor for a perfect fluid, where the particles are stationary in space but exert constant pressure on each other. There are many other types of energy-momentum tensors that I won't get into in this video. So, to summarize this video, we wanted to generalize the concept of mass density to something that's invariant under Lorentz transformations, and doesn't change even with the effects of time dilation and length contraction. We started with the concept of number-flux 4 vector. The time component counts the number of particles in a spatial cube at a moment in time, and the 3 spatial components count the number of particles crossing a unit square over a unit time, which is kind of like a unit cube with 2 space dimensions and 1 time dimension. So the concept of spatial density and current density are all unified as one idea, counting the number of particles in a 3D box in 4D spacetime. We then generalized this idea of counting particle flux across a 3D unit cube to counting the amount of 4-momentum contained in a 3D unit cube, which gave us 4 times 4 equals 16 components. Since for each of the 4 cubes we could draw in spacetime, we could count one of the 4 components of 4-momentum. This symmetric 4x4 matrix is called the energy-momentum tensor, and it is the correct generalization of mass density for special and general relativity. We also found we could write a law of conservation of 4-momentum by saying the divergence of this tensor is 0. Now that we've generalized the mass density to the energy-momentum tensor, in the next video we're going to generalize Poisson's equation to the Einstein field equations, which are the main equations for our relativistic theory of gravity called general relativity.